You ever stop and think about the huge, perfect sheets of glass on our skyscrapers, or even the windshield in your car? It's a technology that's so good, so revolutionary, that it's become completely invisible. We just take it for granted. Well, today, we're going to pull back the curtain on the incredible story of float glass. So let's get right to it. The big question is this: how did we go from glass that was all wavy and distorted to the absolutely flawless panes we see everywhere today? I mean, the leap was enormous, and trust me, the answer changed our world. All right, let's turn back the clock. Before the 1950s, if you wanted a big, clear sheet of glass, you had a problem. You basically had two options, and honestly, neither of them was great. It was a classic case of being stuck between a rock and a hard place. So on one hand, you had what was called sheet glass. Sure, it was affordable to make, but looking through it was like being in a funhouse. The view was all warped and wavy. Then you had the high-end stuff, plate glass. It was beautifully clear, but making it was just a brutal, incredibly expensive process that involved grinding and polishing both sides down mechanically.
And get this, the sheer wastefulness of that old plate glass method was just staggering. They would literally grind away up to 20% of the glass, turning it into dust just to get it flat. Think about that for a second. A fifth of your material, your energy, your money, just gone.
You can see why the whole system was just begging for something better. And that something better didn't come from just improving the old ways. No, it came as a complete, out-of-the-blue paradigm shift, a moment of pure genius that basically threw the old rulebook out the window. The inventor, Sir Alistair Pilkington, had this flash of insight that was totally counterintuitive but absolutely brilliant. He realized that to make a perfectly flat solid, you don't grind it flat. You form it on something that's already perfectly flat, a liquid. That was it. That was the mental leap that changed absolutely everything. And this wasn't an idea that just sat on a shelf for decades. The light bulb went off in 1952, and by 1959, it was a real commercial process. In just 7 years, this radical new way of thinking started its takeover of the entire global glass industry. That's lightning fast. Okay, so a brilliant idea is one thing, but how do you actually do it? How do you turn it into a real-world industrial process? Well, you build something that sounds like science fiction, a machine that creates a continuous, literally endless river of perfect glass. Let's look at how it works. When you boil it down, it's really a three-step dance. First, you melt a massive amount of raw materials, sand, soda ash, that kind of thing. Second, and this is the magic part, you pour that molten glass onto a giant bath of molten tin. Finally, you have to cool the whole thing down very, very slowly in a process called annealing, which gets all the stress out of the glass so it doesn't just shatter. And just to give you an idea of the kind of heat we're talking about, the furnace, which can hold 2,000 tons of material, runs at over 1,500 degrees Celsius. That's actually hotter than volcanic lava. It's just incredible. The scale of this whole operation is mind-boggling. A single float glass production line is this enormous, continuous machine stretching nearly half a kilometer. And it never stops. It runs 24/7 for 10 to 15 years at a time before it gets shut down for maintenance. Now, the big idea of floating glass on liquid sounds simple enough, but as they say, the devil is in the details. Making this process actually work perfectly meant solving some really fascinating and difficult physics and engineering challenges. So you might be wondering, why tin of all things? Well, tin is pretty much the perfect candidate for a few key reasons. 1, it's denser than glass, so the glass just floats right on top. 2, it stays liquid across the huge temperature range you need for this to work. And 3, and this is crucial, its surface tension is so high that it creates an almost perfectly flat mirror-smooth surface for the glass to form on. When you pour the molten glass onto the tin, there's this little tug of war that happens. Gravity is pulling the glass down, trying to spread it out, while the glass's own surface tension is trying to pull it back together. The point where those two forces find a perfect balance creates a natural, or equilibrium, thickness. And as it turns out, that natural thickness is precisely 6.9 millimeters, which is a really cool discovery, but it was also the first big hurdle for the process. What if you need much thinner glass for a car window, or much thicker glass for a security barrier? 6.9 millimeters just wasn't going to work for everything. And this is where the engineers got really, really clever. To make the glass thinner, they use special top rollers that gently grip the edges of the glass ribbon and stretch it out while it's still soft. And to make it thicker, they put in special barriers that don't stick to the glass, restricting its spread and basically letting it pile up on itself before it hardens. Okay, one last critical detail. Hot tin and oxygen are mortal enemies. If they meet, they form tin oxide, which creates defects on the glass. The solution? Get rid of all the oxygen. The entire float bath is sealed in a controlled atmosphere of nitrogen and hydrogen. That little bit of hydrogen acts like a security guard, seeking out and combining with any stray oxygen molecules to keep the tin surface absolutely pristine. So once they mastered all these little details, the float process did so much more than just make better glass. It literally enabled a new kind of world. It kicked off a revolution in transparency that we are very much still living in today. The beautiful payoff for all this work is what they call a fire polish. The surface of the glass is perfectly smooth because it was formed on the undisturbed surface of a liquid. That incredibly wasteful, expensive, and time-consuming step of grinding and polishing, it was just gone, eliminated. And that single change started a huge domino effect. The cost of perfect glass plummeted. It made the modern era of glass-clad skyscrapers possible. It gave us the high-quality foundation for today's safe laminated windshields and even things like bulletproof glass. Put it this way, our entire modern world looks the way it does in large part because of this one process.
You know, whenever you see a modern city skyline, it's just dominated by these incredible glass skyscrapers. Have you ever just stopped and wondered, how? I mean, really, how do they work? How can you wrap a whole building in glass? Well, the answer is pretty amazing, and it's hidden in some of the most fascinating and frankly invisible engineering out there.
So we're going to get into the two massive questions that architects and engineers had to solve. First, with all that sunlight pouring in, why don't these buildings just turn into giant ovens and cook everyone inside? And second, when you get hurricane-force winds hundreds of feet up in the air, what in the world keeps those massive sheets of glass from just shattering into a million pieces? Okay, so this whole story really kicks off back in the 1960s and 70s. Architects at the time were totally obsessed with this new modernist ideal. They had this dream of creating buildings that felt, well, dematerialized. They wanted them to look sheer and light, almost like they weren't even there.
And for the very first time, this dream actually seemed like it could become a reality. See, the float glass process had just been standardized, which meant that suddenly you could manufacture these enormous, perfectly flawless panes of glass. The stage was set to build these perfect, seamless, transparent towers. But as you can imagine, they were about to hit a pretty major roadblock.
Yeah, it turns out that when you build a house, or in this case a skyscraper, entirely out of glass, you don't just get a building, you get a greenhouse. A huge, people-filled greenhouse just sitting there baking in the sun all day long. And this became the first massive crisis for the all-glass building. So you had this epic clash between the architectural vision and, the laws of physics. The dream of a light, transparent skin came with what they called a severe thermal penalty. All that solar heat would pour in through the glass, get trapped inside, and it forced these buildings to rely on absolutely gigantic, energy-devouring air conditioning systems just to make them livable. The dream was kind of turning into an environmental nightmare. The solution that ultimately saved the glass skyscraper wasn't some big, bulky thing you could see. Nope, it was an invisible shield, something engineered at the atomic level that would completely change the game for what glass could do. The breakthrough was this process with a very long name, magnetron sputtering vacuum deposition, or MSVD for short. It sounds complicated, but here's the gist. You take a huge sheet of glass, you slide it into this massive vacuum chamber, and then you use super hot plasma to basically spray atoms of metal, and this is the key part, silver, onto the surface of the glass. It creates this perfectly even coating that's unbelievably thin. And we're not just talking about one single layer here. Engineers developed what they call a stack, which could have 12 or even more different microscopic layers. You've got base layers, barrier layers, but the real hero, the absolute engine of this whole thing, is a layer of pure silver, just a few atoms thick. The result of this was nothing short of revolutionary. That tiny silver layer is basically transparent to visible light, but to infrared radiation, which is just heat, it acts like a mirror. So all of a sudden, you could have a glass facade that lets in 70% of the daylight, making the inside feel open and bright, while at the same time rejecting more than half of the sun's heat. They had literally figured out how to decouple light from heat. Problem number one, solved. Okay, so they solved the heat problem. But that just made the second challenge stand out even more. These buildings weren't just sitting in the sun, right? They were getting absolutely hammered by incredible wind forces, especially the higher up you go. I mean, we are talking about pressures that can be more than 100 pounds pushing on every single square foot of glass. Now just picture how big some of those windows are. The total force is just mind-boggling. So the next giant question for the engineers was, okay, how do we even attach these things to the building? The old ways just weren't going to cut it. The forces were way too big, and besides, the architects definitely did not want big, bulky metal frames messing up their perfect, uninterrupted glass skin. And the solution was, once again, almost totally invisible. It wasn't mechanical, it was chemical. It was a complete revolution in how we stick glass onto buildings. So the traditional way was something called captured glazing. Basically a visible metal frame that holds the glass panel on all four sides. But to get that seamless all-glass look, engineers turned to structural silicone glazing. Instead of a mechanical frame, the glass was literally bonded or glued directly to an internal support structure using these incredibly high-strength silicone sealants. The load from the wind was now being transferred through chemical adhesion, and that finally gave architects that uninterrupted skin of glass they always dreamed of. The Willis Tower in Chicago is just a perfect real-world example of this. The engineers knew that the glass itself was actually pretty flexible, so they designed the whole system to allow those huge panes to bow inwards and outwards under the wind load without putting any stress on the edges of the glass, because that's where it's most likely to break. It's really this incredible dance between strength and flexibility. And they couldn't just guess about these forces. Engineering for towers like the original World Trade Center required a ton of wind tunnel testing. And this was so important for understanding not just the pressure pushing on the front of the building, but also the negative pressure, the suction force on the sides and the back, which, get this, can actually be double the force of the wind hitting the front. So when you put these two revolutions together, you get the modern glass skyscraper that we know today. It's a building that looks impossibly light and simple from the outside, but it's really held up by this incredibly complex, totally hidden science. So in the end, the all-glass tower really stands as a monument to these two invisible revolutions. First, you have atomic-level coatings that tame the sun by splitting light from heat. And second, you have advanced chemical adhesives that tamed the wind, basically turning a fragile material into a key structural part of the building's skin. Think about glass for a second. You know, it's the very symbol of fragility, right? But what if I told you that when you engineer it just right, it can become a fortress? So how in the world do we get from something that shatters so easily to something that's, well, fortified? Let's dive in.
Yeah, that's the big question, isn't it? How can something so fragile, something we're always told to be careful with, stop a military-grade bullet? It just sounds impossible. But the science behind it? Wow. It's an absolute masterclass in taking a fundamental weakness and flipping it into an incredible strength.
And here's a little spoiler alert for you. The answer isn't some single magical invention. It's a story. It's a story of layered innovation. Engineers just kept adding one solution on top of another, building up this defense to defeat bigger and bigger threats. So that's what we're going to do. We're going to peel back those layers one by one. Okay, so before we can even think about stopping bullets, we have to rewind a bit. We've got to solve a much more basic, everyday problem, just making glass safe, for cars, for buildings. So let's start at the very beginning. Right, so your standard run-of-the-mill annealed glass, when it breaks, it creates these deadly, jagged shards. Daggers, basically. And you can imagine, in a car crash or even just a broken window at home, that's a massive, unacceptable danger. It's problem number one that engineers had to fix. So, what's the first solution? It's a process called tempering. And the best way to think about it is like giving the glass its own invisible suit of armor. Seriously, this armor is created by putting the outer surface of the glass under a ton of compression. And how do they forge this armor? It's all about heat and cold. First, they heat the glass up to about 620 degrees Celsius, so it's almost soft. Then, bam! They blast it with jets of cold air. The surface cools and hardens instantly, but the inside is still hot and cools down way slower. This creates this insane tug-of-war, putting the outside under massive compression. So what happens when it finally breaks? All that pent-up energy releases at once, and it just disintegrates into these little, blunt, relatively harmless cubes instead of sharp daggers.
Okay, so that's great for breaking safely, but what if you don't want the glass to break apart at all? What if you want it to hold together? Well, that brings us to the second big idea, lamination. And this one is kind of like a super strong, totally transparent safety net. It's a tough, elastic polymer, usually something called PVB, that gets sandwiched between two layers of glass. So you see, we've got two totally different paths to safety here. You've got tempering, that's your car's side windows, which is all about braking safely. Then you have lamination, that's your windshield, which is all about holding together and stopping stuff from getting through. These two ideas, they are the absolute bedrock for everything we're about to get into.
All right, so we've got the basics down. Now, how do we escalate from everyday safety to, actual ballistic security? Well, engineers started combining these ideas, and that's when things got really interesting.
The early attempts, right after World War II, they were pretty crude. We're basically just talking about super thick stacks of laminated glass, and you can imagine the problems, right? They were insanely heavy. They had that classic green Coke bottle tint that made it hard to see clearly, and the layers would start to peel apart over time. I mean, they kind of worked, but they were a long, long way from perfect. But then, things really started to accelerate. After those clunky early days, the 1980s hit, and bam! A total revolution with a new composite material. Then, into the 90s, things got standardized. We got actual ratings, so for the first time you could know exactly what level of protection you were buying. And this composite material, this was the real game changer. It's called Glass-Clad Polycarbonate. Instead of just piling on more and more heavy glass, engineers got clever. They created a team of materials. The hard outer glass layer is like the first line of defense. Its only job is to hit the incoming bullet and deform it, flatten it out. Then, the tough, kind of flexible polycarbonate layer behind it acts like a catcher's mitt. It gives a little, absorbing all that insane kinetic energy and stopping the bullet cold. But here's where the story takes a twist. Just when engineers thought they had it figured out, a new hidden danger popped up. Because, as it turns out, just stopping the bullet, that was only half the battle. I mean, think about this for a second. The bullet is stopped. It never reaches you. You're safe from the attacker, but you could still be in mortal danger from the very thing that's supposed to be protecting you. This is a phenomenon called spall. When the bullet hits the outside, it sends a massive shockwave ripping through the glass. When that wave hits the inner surface with nothing behind it, it literally blasts a cone of high-velocity glass shrapnel inside the vehicle. So even though the bullet is stopped, you get hit with a spray of glass fragments. A truly terrifying secondary threat. So how do you fix that? Well, the solution was actually kind of elegant and beautifully simple. You add one more layer. A final, thin sheet of polycarbonate on the very inside face. We call it the spall shield. And get this, its job has nothing to do with stopping the bullet. That's already been taken care of. Its only job is to flex, like a trampoline, and catch all of that dangerous glass shrapnel. It's the last line of defense, and it's absolutely critical. Okay, so we've got all the pieces of the puzzle now, right? We have tempering, lamination, the polycarbonate core, and the spall shield. Let's put it all together and see how it creates a true transparent fortress in a modern armored car.
So when you look at a modern armored window, it's this incredibly complex sandwich. You've got layer 1, the hardened glass strike face out front, ready to flatten the bullet. Then you've got layer 2, which is actually multiple layers of glass and that PVB polymer, all working to soak up the energy. And finally, layer 3, that all-important polycarbonate spall shield on the inside to protect the people. It's a perfect system where every single layer has one specific, crucial job to do.
And the end result is just incredibly thick and robust. For high-end protection, like for an executive limousine, we're talking about glass that's anywhere from 40 to 70 millimeters thick. I mean, let that sink in. That's almost 3 inches of transparent armor. And the performance? It's just staggering. We are not talking about stopping little handguns here. This kind of protection is engineered to take multiple hits from a high-powered 7.62 millimeter NATO military rifle and just shrug them off.
But, just making the glass is only one part of the challenge. Now you have to actually integrate it. Think about it. Problem? A window now weighs hundreds of pounds. Solution? You need heavy-duty hydraulic lifts and reinforced door hinges just to open it. Problem? That old Coke bottle green tint. Solution: you use special high-purity, low-iron glass for better clarity. And the biggest one. Problem: how do you stop bullets from slipping through the gaps in the frame? Solution: use these clever stepped-edge designs that create a perfect, seamless ballistic seal.
And that right there is why you can't just take a normal car and swap in armored windows. The whole vehicle has to be completely re-engineered from the ground up, all to support the glass. It's a complete systems engineering approach from start to finish.
So let's bring it all back to that first question. The crucial takeaway here is that transparent armor isn't one single thing. It's a system. It's an evolution of layered solutions, starting with tempering and lamination, moving to that glass polycarbonate composite, and finishing with that life-saving spall shield. They're all working together like a highly engineered symphony to defeat ever-escalating threats.
You know, it's kind of funny. We look through windows every single day, but have you ever really thought about what you're looking through? It just seems so simple. So basic, right? Well, that perfect clear sheet of glass is actually the result of this incredible hidden chemical recipe. A recipe that's been tweaked and perfected over a century to solve one problem after another. So let's pull back the curtain and really dig into the secret chemistry that turns a pile of sand into the flawless window panes we take for granted. So what is that secret recipe? What really makes glass? Well, glass. It's a story of chemical problems and some absolutely brilliant solutions. It's like a high-stakes balancing act, all happening at scorching hot temperatures. And our story starts with the glassmaker's biggest headache. All right, so our journey begins with this really fundamental problem. The main ingredient for glass, as you probably know, is sand. And sand is mostly just a chemical called silica. But that super simple starting point, it presents a massive dilemma for anyone who wants to make glass. And here's that dilemma in one number. Over 1,700 degrees Celsius. That's more than 3,000 degrees Fahrenheit. That is the ridiculously, impractically high temperature you'd need to melt pure sand. I mean, can you imagine trying to run a factory at those temperatures? It would be crazy expensive and unbelievably difficult. It's not gonna work for mass production, no way. So, chemists came up with this brilliant little hack. They started adding something called soda ash. Now, in chemistry, this acts as a flux, and you can think of it like a chemical crowbar. It literally wedges itself into the super tight structure of sand, prying it apart and making the whole thing melt at a much, much more manageable temperature. This one simple addition is what makes industrial-scale glass production even possible. But, and here's the crazy twist, in solving that temperature problem, they created a totally new and frankly catastrophic one. The very same thing that made the glass easier to melt, that soda ash, also made it soluble in water. Yeah, you'd have a window that could literally dissolve in the rain. They actually called it water glass, and as you can imagine, it was completely useless for, buildings. So that failure led to the next chapter in our chemical story, the search for a recipe that would actually create stability. The big question was, how do you keep that awesome low melting point but make the final product strong and durable enough to last for decades? And the solution was to add two more key ingredients into the mix, limestone and dolomite. These guys act as stabilizers. They introduce chemicals like calcium oxide and magnesium oxide, and these new components basically go in and rebuild the glass's chemical defenses, making it super strong and resistant to water. This is what gives glass its toughness, its durability. And this right here is the result. This is the final globally standardized recipe. It's called Soda-Lime-Silica glass, and it makes up pretty much all the windows in the world. As you can see, about 72% is still our main ingredient, silica from sand. Then you've got about 14% soda to help it melt, and around 12% lime and magnesia for that all-important durability. So let's just quickly recap what each part of the team is doing. You've got silica, which forms the basic structure, the backbone. Sodium oxide is the flux, a total game changer for lowering the melting point. Calcium oxide brings the durability, and then that little bit of alumina helps fine-tune everything else. Every single component has a critical job to do. It's a real team effort. But here's something you might not think about. The perfect recipe isn't just about the final product you hold in your hand. It also has to be perfectly tailored for the manufacturing process itself, specifically for the modern float glass method, where this long ribbon of molten glass is formed on a perfectly flat bed of molten tin. And that whole process hinges on one critical property, viscosity. Basically, how runny the molten glass is. The chemical recipe has to get this perfect at every single stage. So in the furnace, it needs to be really fluid and runny so bubbles can escape. Then on the tin bath, it has to be just right to spread out into a flawless, even ribbon. And finally, at the exit, it needs to be just stiff enough to be lifted away without breaking or warping. The chemical recipe is what controls this whole delicate dance. Okay, so we've got strong, durable glass that we can mass produce. Awesome. But what about making it perfectly clear? Well, that brings us to our next chemical quest, the big battle for ultimate clarity. You see, the great enemy of clear glass is this tiny little impurity that's found in almost all sand, iron oxide. You probably know it better as rust. And even in the tiniest amounts, it gives glass this distinct green tint. You've probably seen it yourself if you've ever looked at a thick piece of glass from the side. You can see that green color really clearly. So to deal with this green tint, manufacturers came up with two different strategies. The first one, for standard glass, is pretty clever. You just mask the iron. The second strategy, which is for that high-end premium glass, is to get rid of the iron completely. Let's take a look at that first strategy, because it's really cool. It's this fantastic little trick that's all based on color theory. So to cancel out that green from the iron, chemists add tiny, super precise amounts of selenium, which creates a kind of pinkish red color, and cobalt, which creates a blue hue. Since those colors are complementary to green on the color wheel, they all mix together and cancel each other out, creating a neutral gray. And to our eyes, that neutral gray just registers as clear. It's an optical illusion right in your window. Okay, there's just one final hurdle in our quest for perfect glass. The melting process itself can trap teeny tiny gas bubbles, and those bubbles, of course, ruin the clarity. So what's the final chemical trick they use to get that perfectly bubble-free finish? Well, this bubble removal process is called fining, and the chemicals they use for it have definitely evolved over time. Back in the mid-20th century, a really common fining agent was arsenic trioxide. It worked great, but it was highly toxic. So naturally, concerns for safety and the environment led to a big shift towards using sodium sulfite instead, which is much, much safer. But, and there's always a but, right? This safer option is a lot trickier to use. It requires incredibly precise chemical management of the furnace's atmosphere. The process is called redox control, and it's all about controlling the oxygen levels. If the conditions are just a tiny bit off in one direction, what they call too reducing, the glass can turn an ugly brown. And if it's a little off in the other direction, too oxidizing, then the bubbles don't get removed at all. It is a constant chemical tightrope walk. The secret to the flawless glass that's literally all around us, it's not just about melting down sand. It's about a full-blown digital revolution that had to happen completely behind the scenes just to make something we take for granted. So where did this all begin? Well, like a lot of great innovations, it started with a massive, massive problem. As manufacturing got faster and more efficient, glass producers hit a wall, or maybe more like a barrier made of pure, unstoppable speed. I want you to really think about this for a second. Picture yourself in a factory. There's a ribbon of hot, fresh glass wider than a car, and it is streaming past you faster than you can sprint. Your one job? Find a flaw that's pretty much invisible. How on earth do you do it? And listen, that is not an exaggeration. We're talking about a relentless flow of glass, moving at 20 meters every single minute. At that kind of velocity, trying to use the human eye for quality control wasn't just inefficient, no, it became physically impossible. They absolutely needed a new way.
So okay, if a human eye couldn't keep up, the industry had to invent a totally new kind of eye. One that was faster, way more precise, and, never blinked. They had to build a digital eye.
And this is where the genius of laser scanning comes into the picture. The idea is actually super elegant. You shoot a laser beam across the surface of that moving glass. Now, if the glass is perfect, the light just zips right through. But if it hits an imperfection, even a tiny one, that light scatters. And that little scatter, that's the signal. So here's the play-by-play. You have a rotating mirror that sweeps a laser back and forth across the glass thousands of times a second. When that light hits a defect, it scatters. Super sensitive sensors pick up that scattered light, and a computer instantly, and I mean instantly, creates a defect map, pinpointing every single flaw in real time. And the level of precision we're talking about here is just staggering. This system could reliably spot flaws as tiny as 0.1 millimeters. To give you some perspective, that's about the thickness of a single human hair, spotted on a giant sheet of glass that's flying by. Wild. So what's it actually looking for? Well, these tiny imperfections could be anything. Microscopic gas bubbles trapped inside, tiny unmelted bits of sand they call stones, or even minuscule drips of tin left over from the manufacturing process. These are all flaws no human could ever hope to spot consistently.
Okay, so now you've got this perfect map of every single flaw. That's amazing data, right? But data is only useful if you can actually do something with it. And that brings us to the next brilliant phase of this whole thing, the intelligent cut.
This is where the whole system gets truly smart. That digital eye sends its defect map over to a digital brain. It's a computer numerical control system, a CNC machine. Just think of it like this super powerful software whose only job is to look at that map and figure out the absolute perfect decision every single time.
And the difference it made was just night and day. Before this, cutting glass was all guesswork. It led to huge amounts of waste and inconsistent quality. But now, the software analyzes that defect map and instantly calculates the perfect cutting pattern to slice around every flaw. Waste basically disappears, and every single piece that ships out is perfect.
But you know, seeing the flaws and planning the cuts, that's only part of the puzzle. You still have to physically handle these enormous, heavy, and obviously super fragile sheets of glass. And this is where the final piece of the automation revolution clicks into place. You let the robots do the heavy lifting.
The source material we used for this explainer sums it up perfectly. It says this next wave of automation removed the human element from the dangerous heavy lifting. And that's key. This wasn't just about being more efficient, it was about keeping people safe. The benefits were just huge. Worker injuries from handling heavy glass plummeted. Factories could now safely work with these massive jumbo plates that were just way too big and dangerous for people to move by hand. That risky old process of separating sheets, which they called bucking, was totally replaced by automated vacuum lifters and incredibly precise robotic stackers.
So when you step back and look at the whole story, you see this incredible journey of innovation. It all started with an impossible problem, speed. And it was solved by a digital eye that could see the invisible, a digital brain that could think with perfect efficiency, and finally, powerful robots that could do the dangerous work. This whole template of see, think, and act became the blueprint for modern manufacturing, way beyond just glass.
Hey, have you ever stopped to think about the one piece of tech you touch more than anything else all day long? Yeah, I'm talking about the screen on your phone. It just feels like a simple piece of glass, right? But the story of how it got so impossibly thin, so clear, and so tough, well, that's one of the great hidden revolutions of our time. So let's dive in and uncover the secret science that makes it all possible.
To really appreciate just how far we've come, we've got to look back at where we started. And trust me, the past was, well, it was fragile.
Think back to before the first iPhone. The screens on our devices were honestly pretty awful. They were mostly made of cheap plastic, or the same basic soda-lime glass you find in windows and bottles. Keys in your pocket, scratches everywhere. They got hazy, they got cloudy, and they shattered from the smallest drops. They were without a doubt the weakest part of any gadget.
And then everything changed. One single innovation came along that just flipped the script. And the funny thing is, it wasn't the glass itself, but the technology that demanded a totally new kind of glass be invented, or, as we're about to see, rediscovered. See, the invention of the capacitive touchscreen, the kind that magically responds to the light touch of your finger, created this massive new problem. All of a sudden, the screen wasn't just something you looked at. It was the main way you interacted with the device. You were touching it, swiping it, and carrying it everywhere. The old materials just couldn't hang.
And this slide, man, it just perfectly lays out the insane challenge they were facing. The new glass had to be optically perfect for those gorgeous new displays. It had to be a dielectric, basically an electrical insulator, so the screen could actually sense the tiny charge in your finger. And on top of all that, it had to be unbelievably tough. Getting all of those properties into one material was a huge, huge engineering puzzle.
So where did the solution come from? You'd think it was some brand new cutting-edge discovery, right? Nope. The answer was actually hiding in the company archives, a technology that was developed decades earlier for something totally different and then just abandoned. This is one of my favorite parts of the whole story. It's just incredible. Way back in the 1960s, a company called Corning had this top-secret Project Muscle where they developed an ultra-strong glass. They thought it would be great for things like car windshields, but it was just too expensive and way ahead of its time, so they put it on the shelf. Fast forward 40 years, the iPhone happens, and a light bulb goes off at Corning. They realized they were sitting on the perfect solution all along. They dusted off those old formulas, tweaked them for modern tech, and voila, Gorilla Glass was born.
So, what's the secret sauce here? What actually makes this glass so different from the stuff in your window? Well, the secret isn't just what it's made of, but how it's treated in a process that honestly sounds like something out of a sci-fi movie.
The hero material here is called Alkali-Aluminosilicate glass, but the key ingredient you need to remember is aluminum oxide. Here's a way to think about it. Imagine regular glass is like a perfectly smooth, tightly packed brick wall. The aluminum oxide acts like a spacer, intentionally creating these tiny, deliberate gaps in that wall. It opens up the atomic network, and that's what makes all the magic possible.
In that open atomic structure, that is the whole game changer. With regular glass, that network is just too tight. You can't really force anything new into it to make it stronger. But in this special aluminosilicate glass, those gaps are like perfectly designed doorways, ready to allow a radical transformation to take place.
And this is that transformation. It's a process called ion exchange. Okay, so they take the sheet of glass and dip it into this crazy hot bath of molten potassium salt at about 400 degrees Celsius. The little sodium ions that are already in the glass flow out, and bigger potassium ions from the bath rush in to take their place. But since the potassium ions are bigger, they get crammed in there super tightly. This stuffing creates a layer of immense compression on the surface. It's like giving the glass an invisible suit of armor.
But, having an amazing recipe is one thing. You still have to actually make the stuff. And you have to do it flawlessly, which is where the competition really starts to heat up.
So you've got two main ways of doing this. On one side, you have Corning with its unique fusion draw process. Molten glass flows into a trough, overflows, and then the two sheets fuse together in mid-air as they're drawn downward. The key is, its surface is never touched by anything. It's pristine. Most competitors, on the other hand, use the float process, where the molten glass floats on a bed of liquid tin. It's super efficient, yeah, but that contact with the tin can create tiny, microscopic flaws. And for glass, even a microscopic flaw is like a tiny crack just waiting to happen.
And all this has sparked this huge global rivalry. You've got the heavyweight, Corning in the US with Gorilla Glass. Then in Japan, you have AGC making Dragon Trail with that float process. And you can't forget Schott AG over in Germany, who are coming at it from a totally different angle, using lithium in their chemistry. This intense competition is exactly what pushes the technology forward so fast with every new phone that comes out. So we've gone from fragile plastic to these super strong, chemically engineered surfaces. But believe it or not, this is really just the beginning. The exact same science that protects your phone is about to completely reshape our world.
We're at a point now where glass isn't just glass anymore. It's become this incredible platform for nanotechnology. By engineering it atom by atom, we can give it properties that honestly sound like they're straight out of science fiction.
I mean, just look at what's coming down the pipe. We're talking transparent armor that's lighter and stronger than steel. We've got glass so thin and flexible it can be folded in half, which, hey, we're already seeing that in stores right now. There's smart glass that can turn opaque or generate power with the flick of a switch. We're even starting to use glass as a core structural material in massive skyscrapers.
Scientists figured out a way to fundamentally change the properties of the glass surface itself, giving it this incredible, almost unnatural ability to resist damage.
What they do is create this hidden layer, a kind of atomic armor, by putting the very surface of the glass under immense, constant pressure. You can't see it, but it's there, like an invisible force field holding the whole thing together.
So yeah, the secret is stress. And this is what's so wild about it. We think of stress as a weakness, something that causes failure. But in this case, it's the ultimate source of strength. We're talking about a very specific, carefully engineered compressive stress, which, of course, leads to the next question. How on earth do they create it?
Well, this atomic armor is forged using a really brilliant application of physics called the ion exchange process. And we're going to break down exactly how this high-tech recipe for super strong glass works, step by step. It's actually a surprisingly elegant four-step process that transforms a totally normal sheet of glass into that durable screen you've got right there in your pocket.
Here's how it goes down. First, you take a special, really pristine sheet of what's called aluminosilicate glass. Then, you dunk it into a bath of molten salt. This is where the real magic happens, that ion exchange. And finally, you cool it all down, which locks that powerful compressive armor right into place.
And when I say a bath of molten salt, I mean it. This process happens at some serious temperatures. We're talking between 350 and 500 degrees Celsius. That heat is absolutely crucial because it gives the atoms or ions inside the glass enough energy to get excited and start moving around.
And all that mobility on the atomic level sets the stage for the scientific heart of this whole process, what we can call the Great Ion Swap. This is where the real engineering begins.
It all comes down to something called the stuffing effect, and it's pretty much what it sounds like. Think of it like this. Smaller atoms are encouraged to leave the glass, and at the same time, the process forces much larger atoms from that salt bath to squeeze into the tiny spaces they've left behind. It's basically atomic level overcrowding, and it's completely intentional.
To be specific, there are two key players in this atomic swap meet. You've got the smaller sodium ions, which are already hanging out in the glass, and they move out. At the exact same time, larger potassium ions from the molten salt bath get pushed in to take their place.
And just to give you a sense of the scale here, the sodium ions leaving the glass have a radius of about 1.02 angstroms. An angstrom is incredibly mind-bogglingly tiny. It's 1/10 billionth of a meter. So yeah, we are truly talking about engineering at the atomic level.
But check this out, the potassium ions rushing in to replace them are significantly bigger, with a radius of 1.38 angstroms. That tiny fractional difference means everything. It's literally like trying to cram a basketball into a space where a baseball used to be. So here's the payoff. As the glass starts to cool down, its atomic structure naturally wants to shrink and get tighter. But those bigger potassium ions are now wedged into spaces that are way too small for them. They push back, they resist that contraction, and by pushing outward, they create that immense layer of compressive stress we've been talking about. That's our atomic armor.
Okay, so now we know how the armor is actually made. So let's take a look at how this invisible shield works in the real world to stop your screen from shattering. To get how the shield works, you first have to understand one fundamental thing about how glass breaks. Glass is incredibly weak when it gets pulled apart, a force we call tension. Any tiny crack or flaw will spread like wildfire when the atomic bonds at its tip are put under tension and literally ripped apart.
And this is where the genius of the ion exchange process comes in. It builds in this massive compressive shield that's always pushing outwards. So when an outside force, like you dropping your phone, tries to apply tension and pull the glass apart, it first has to fight against and completely cancel out all of that built-in compression. Only then can it even begin to put the glass into tension and actually cause any damage. And we are not talking about a small amount of force here. This compressive shield can be as high as 600 to 1,000 megapascals. To try and put that into perspective, that's up to 10,000 times the atmospheric pressure around us right now. That is a staggering amount of built-in protection.
But as we all know too well, screens can and do still break. So for our final section, let's look at how even this powerful shield can eventually fail.
See, engineers measure the shield's effectiveness using two key metrics. The first is compressive stress, or CS for short. That's basically how strong the shield is. But just as important is the depth of layer, or DOL, which measures how thick that protective armor is. So if a scratch or a flaw in the glass is deep enough to pierce all the way through that depth of layer, it reaches the unprotected, vulnerable core of the glass underneath. And when that happens, all of that stored up compressive energy is released in an instant. And that's when you get that familiar, catastrophic spiderweb shatter across your screen. Of course, this technology is always getting better. Engineers are now using even more complex methods, like using different mixtures of salts in the bath or multi-step exchange processes, all to create even deeper and more robust protective layers. It's a constant effort to make our screens tougher every single year.
The material science protecting our screens has taken a massive, massive leap forward. So to really appreciate just how cool this new super material is, we first have to understand the fundamental problem it was designed to solve. You see, for decades, scientists were stuck with a basic trade-off, a choice between two very different materials, glass and ceramic. And this right here lays out the whole dilemma perfectly. On one side, you've got glass. Its atoms are all jumbled up and chaotic, which is fantastic for transparency. Light passes right through it. But that same randomness makes it super brittle. Then, on the other side, you have ceramic. Its atoms are in this highly ordered, rigid crystal structure. That makes it incredibly tough, but that neat structure also scatters light all over the place, making it opaque.
You can't exactly watch a video through your coffee mug, right?
And here's why that brittleness in glass is such a big deal. When a tiny crack forms in traditional glass, there's absolutely nothing to stop it. It just zips through that random atomic network in a nearly straight line with almost no resistance. And that's how one small drop leads to a catastrophic screen-wide shatter. So the challenge was pretty clear. How in the world do you get the see-through quality of glass and the hardcore toughness of ceramic into one material? For the longest time, it really seemed impossible. But it turns out the answer was a resounding yes. And the solution is a truly amazing material called a glass ceramic. It's not one or the other, it's a genuine hybrid, engineered from the ground up to give us the best of both worlds. And hey, this isn't some futuristic lab experiment we're talking about. It's very likely in your pocket right now. The most famous example is ceramic shield, a material that Apple and the glass wizards at Corning developed, and it's been on iPhones ever since the iPhone 12. So the big question is, how do you actually bake the strength of a ceramic into perfectly clear glass? Well, the process is incredibly clever, and it all comes down to controlling crystals at a scale that is just unbelievably small. Okay, so it all starts with a very special batch of glass. Mixed into this molten glass are things called nucleating agents. You can think of them like tiny little seeds, just waiting for the right signal. And that signal, it comes from a very, very precise heat treatment. This specific wave of heat triggers those seeds, and suddenly, billions of microscopic ceramic crystals start to grow inside the glass matrix itself. But here is the truly brilliant part. These aren't just any old crystals, they're nano-ceramic crystals. The engineers can control their growth so precisely that they stay smaller than the wavelength of visible light. I mean, that is a mind-bogglingly tiny scale to work with. And that is the absolute key to the whole thing. Because these tiny crystals are smaller than the light waves trying to pass through, they don't really interact with them. They don't scatter the light just flows right past, which allows the material to stay crystal clear, even though it's now packed with these incredibly hard, strengthening ceramic structures. Okay, so we've got this transparent material, and it's loaded with these tiny ceramic crystals. But how exactly do those crystals stop that catastrophic shatter we were talking about earlier? Remember how a crack in normal glass just travels in a straight line? Well, in a glass ceramic, when a crack starts, it almost immediately runs smack into one of these nanocrystals. And that crystal is basically a microscopic roadblock. The crack can't go through it, so it's forced to change direction, it has to deflect or branch off, or it might just stop dead in its tracks. This whole process creates what scientists call a tortuous path. So instead of one single easy fracture, the crack has to navigate this minefield of tiny obstacles. And every single time it has to change direction, it loses energy. This dissipates the force from the initial impact, and it essentially just tires the crack out, stopping it long before it can cause a full-on shatter. And as if that wasn't already enough, there's actually a second layer of protection. The glass surrounding all those crystals is also chemically strengthened. It's a process that basically crams larger atoms into the surface to create this super compressed, tough outer skin. It just makes the entire structure that much more resilient. So what does all this incredible science, the nanocrystals creating an obstacle course, the chemically strengthened glass, what does it all actually mean for you and your phone when it takes that inevitable tumble? It means this: 4 times greater drop performance. Now that's not just a small improvement, that is a massive, generational leap in durability, all thanks to our ability to control matter at the nanoscale. So the big takeaway here is this perfect partnership. You have the hard ceramic nanocrystals acting like tiny bodyguards, deflecting any cracks that form, while the tough, strengthened glass all around them acts like a cushion, absorbing the impact. It's 2 different materials working together to become something way, way stronger. You've seen the foldable phones, right? And you've probably wondered the same thing I have. How on earth do you take a solid sheet of glass and just fold it in half, over and over again? It seems like it should be totally impossible, but it's not. So let's get into it. We're going to uncover the secret material that makes all of this technological magic happen. And that brings us to the big question, the absolute mystery at the heart of this whole thing. How can solid, rigid glass just fold up without shattering into a million pieces? Well, the answer is this really cool mix of basic physics and some incredibly clever engineering. You have to appreciate the challenge here. I mean, it was huge. The next wave of gadgets demanded a screen that could bend to a super tight radius, like just a few millimeters, and do it hundreds of thousands of times without failing. This just flies in the face of everything we think we know about glass.
But what's so cool is that the answer isn't some crazy new material from another planet. Nope, the first part of the secret is just pure fundamental physics. It turns out, if you want to make glass bend, you just have to make it really, really unbelievably thin. And that leads us right to the hero of our story today, ultra-thin glass, or UTG for short. This stuff is exactly what it sounds like. It's a special kind of glass, but it's been engineered to be so incredibly thin that it starts to bend and flex like plastic, all while keeping that hard, smooth feel of real glass.
So, just how thin are we talking about here? Well, the magic number, the thickness that makes this all possible, is right around 30 micrometers. And let me tell you, that is a scale that is so small, it's almost impossible to really wrap your head around. But let's try to put it in perspective. At 30 micrometers, a sheet of this ultra-thin glass is about as thick as a single human hair. Seriously, think about that. A sheet of actual solid glass that's as thin as one strand of your hair. It's wild. So how does being that thin actually help? Okay, think about bending a big, thick textbook. The front and back covers have to stretch a lot to make that bend, right? They're under a ton of stress. But now, imagine just bending a single page from that book. It barely has to stretch at all. It's the exact same idea with glass. By making it ridiculously thin, you massively reduce the amount of stress on its outer surfaces when it bends. And less stress means it doesn't break. This quote here just nails it. At that tiny 30-micron scale, the material's properties totally change. It stops acting like the brittle, fragile solid we're all used to, and starts behaving a lot more like a flexible but still stiff piece of plastic. Okay, so we get the what, make it super thin. But that brings up the how. I mean, how in the world do you manufacture a perfectly flawless sheet of glass that's as thin as a human hair? Well, this is where the engineering has to reach a whole new level of insane precision. It all starts, as you'd expect, with molten glass. From there, it goes through what's called a drawing process. Basically, using a careful combination of gravity and precision rollers, the liquid glass is pulled downward, stretching and thinning out as it cools, until you're left with this perfectly uniform, ultra-thin sheet. Now, a really key innovation here is something called the fusion draw process. The absolute genius of this method is that as the glass is being formed, its surfaces never actually touch anything. They just float on air as they cool. The result is a pristine, absolutely flawless surface. And that is so important, because even a single microscopic flaw, something you could never see, can act like a tiny crack, creating a weak point that causes the whole thing to shatter when it's folded. So now we have this impossibly thin, perfectly flawless sheet of glass. We're done? Problem solved, right? Well, not quite. Turns out when you make something this thin, you create a whole new bunch of problems you have to solve. Which brings up a pretty obvious question, one you're probably thinking right now. If this glass is really as thin as a hair, doesn't that make it super fragile and easy to break? And the answer is, yes it does. On its own, this paper-thin sheet is incredibly delicate. Even the tiniest little imperfection, something you can't even see with a microscope, can be enough to cause it to fail under the stress of being folded over and over. So thinness by itself, it's not going to be enough for a phone you carry in your pocket. So, to take this fragile sheet and make it tough enough for you and me, engineers came up with this really clever two-part solution. First, they strengthen the glass chemically, and then they add a protective polymer layer right on top of it. It's a 1-2 punch. The first step is what they call an intensifying process. It's a special chemical bath that basically creates this super compressed layer on the surface of the glass. You can think of it like an invisible suit of armor that massively boosts its strength without bending or warping it at all. And the second part of the solution is a polymer composite. A special kind of plastic resin is coated onto the glass. This creates a laminate system that acts as a shock absorber for impacts, and, as a bonus, it helps contain the glass if it ever were to break. So you take the ultra-thin glass, you add the chemical strengthening, and then you put on that polymer layer. And what you get is the final product. It's a true composite marvel, something that perfectly balances two properties that should be complete opposites. Samsung's marketing team actually came up with the perfect name for it. They called it tough yet tender.
And honestly, that just brilliantly captures what this material is all about. It's tough enough to survive in your pocket, but it's tender enough to literally fold in half. The real genius here is in how these layers all work together as a team. The polymer layer gives it that toughness, that impact absorption, but the ultra-thin glass on top is what gives you that perfectly smooth, hard, scratch-resistant surface that feels like a real premium phone screen, and crucially, it resists getting a permanent crease. And the final result is just incredible. This composite material can survive hundreds of thousands of fold cycles in lab tests. It's just a mind-boggling testament to the engineering that took something so fragile and turned it into a resilient piece of tech we use every single day.
So how do you take a material that's famous for being brittle and turn it into the actual backbone of a skyscraper? Well, that's the puzzle we're going to solve.
So the first giant leap forward was this total shift in thinking. For centuries, glass was just infill. It was something you put in a hole in the wall to keep the weather out. But now it's becoming the wall itself. And sometimes it's even the skeleton.
And to make that happen, the scale had to change, like dramatically. We're not talking about your average window here. The industry is now cranking out what they call super jumbo glass panels that can be up to 20 meters long. I mean, that's the length of a bowling alley.
These massive panels, they aren't just for looks. No way. They are the frame. You go into these flagship stores, these incredible modern buildings, and you'll see glass fins and beams that are literally holding up the roof. They're engineered to handle insane forces like hurricane-force winds.
So how in the world do they make it that strong? Well, the secret is a technology called lamination. This isn't just a single piece of glass. It's a composite material. Think of it like a high-tech sandwich, made of multiple sheets of glass, all bonded together by this super strong polymer inner layer. It's actually a really simple but totally brilliant idea. You take a layer or ply of glass, you add that high-strength inner layer, and then you stick another ply of glass on top. And you can keep stacking these to create these incredibly tough panels that behave in a completely different way than just a single sheet of glass ever could.
And this right here, this is the absolute core safety principle, redundancy. See, because glass is brittle by nature, you have to design it assuming it will fail. With lamination, if one of those layers breaks from, say, an impact, the whole structure doesn't just catastrophically collapse. The other layers and that amazing interlayer just hold everything together, and they keep supporting the weight. The whole point is that it's fail-safe.
All right, so problem one is solved. Glass is now strong enough to be the structure. But of course, that just creates a whole new problem. A wall of glass can be a complete nightmare for energy bills because glass is naturally a terrible insulator. So how do you fix that? Well, the solution is this incredible leap in technology called vacuum insulating glass, or VIG for short. The concept is pure genius. It basically turns your window into a giant flat thermos. You've got two panes of glass separated by a tiny vacuum, which almost completely stops heat from moving through.
And the results are just staggering. Just look at this comparison. A VIG unit that's less than 10 millimeters thick, we're talking thinner than your phone, can have the same insulating power as a triple glazed unit that's 3 times thicker. In fact, its insulation value is comparable to a thick masonry wall. Just let that sink in. A perfectly clear wall that can keep you warmer than a brick wall. That is a total game changer.
But creating that perfect vacuum introduces a brand new, massive force. With no air on the inside pushing back, you have the full weight of Earth's atmosphere just crushing down on the outside of that glass. We're talking about 10 tons of pressure on every single square meter.
So you see what's happening. You've solved the insulation problem, but now you have this immense mechanical problem. With all that pressure, what on earth stops the two panes of glass from just slamming into each other and shattering into a million pieces?
The solution is just so elegant, and it's almost invisible. Engineers place this tiny grid of microscopic support pillars right there in the vacuum between the two panes. And these pillars, they're made of high-strength steel or ceramic. They're only about 0.5 millimeter wide, but they are strong enough to hold that glass apart against all that crushing force.
But placing these pillars is this incredibly complex puzzle. It's a huge optimization problem. If you put them too far apart, the glass is going to bend inward and break. But if you put them too close together, the pillars themselves start conducting heat, acting like these tiny little thermal bridges that completely defeat the whole purpose of the vacuum in the first place. It's an incredibly delicate balancing act. And then, finally, you have to seal the whole thing. And that vacuum, it has to hold for decades, so the seal has to be absolutely perfect.
Now, the old way of doing this involved melting glass paste at really high temperatures, but that process would actually weaken the modern super strong tempered glass. So today, they use advanced techniques like precision laser sealing to create a perfect, long-lasting bond without compromising any of the glass's strength.
Okay, so we've made glass strong, and we've made it a super insulator. So what's left? The final frontier is making it smart. And this is where glass goes from being just a passive material to being an active surface that can literally react to its environment. This technology is called electrochromic glass. And what it does is, by applying a tiny little electrical voltage, you can make the glass switch from being perfectly clear to a dark tint just on demand. This gives you dynamic control over sunlight and heat with no need for blinds at all. Now, the easiest way to get your head around how this works is to imagine a battery that's completely transparent. Seriously, the entire mechanism is built from these ultra-thin layers that are deposited directly onto the glass surface itself.
It's a 5-layer stack. You've got conductive layers on the very outside that apply the voltage. Then in the middle, you have the active electrochromic layer. That's the part that actually changes color. Then there's an ion storage layer that holds the charge, and an electrolyte that lets the ions move between them.
So here's how it actually tints. When you apply a low voltage, like a tiny one, these little particles called lithium ions get pushed from that storage layer into the electrochromic layer. This literally changes the material structure, which makes it absorb light and turn dark. You reverse the voltage, the ions move back, and poof, the glass becomes clear again.
But the precision you need to make this work is just mind-boggling. Every single one of those 5 layers has to be put down with uniformity controlled to the nanometer. We're talking atomic scale. Any tiny little variation across a massive sheet of glass would cause these ugly blotches or uneven tinting. It has to be perfect.
So, when you put all of this together, the strength, the insulation, the intelligence, it's pretty clear we're not just talking about better windows anymore. This is a fundamental redefinition of what glass even is and what it can do.
So, let's just recap this whole revolution real quick. Glass has gone from a fragile pane to a structural behemoth. It's gone from being a massive energy leak to an invisible thermal wall. And it's gone from a passive window to an active thinking surface.
Okay, so what if I told you there's a shield out there that's as clear as glass, but literally as tough as a sapphire? You might think that's something straight out of science fiction, right? Well, it's not. It's the incredible reality of transparent ceramics, and we're about to dive into exactly how this stuff works.
So that leads us to the central question, the one that really drives this entire technology. How in the world do you make armor that's see-through like a window, but has the punch-stopping power of a gemstone? The answer, as you'll see, required a total rethink of material science.
But, to really get why this stuff is such a big deal, we gotta look at the old way of doing things. We need to talk about the huge problems with what it's replacing. Good old traditional armored glass.
See, the old school approach to stopping bullets with glass was pretty simple. Just make it thicker and thicker and thicker. To stop modern threats, you end up with these absurdly thick, heavy slabs of glass. We're talking about a crippling amount of weight that just kills a vehicle's performance, its speed, its agility, everything.
And when you put it side by side, the difference is just, wow. It's not just about the weight and thickness. The real Achilles heel of traditional glass is what happens after it takes a hit. Just one impact can create this massive spiderweb of cracks, right? Suddenly, the people inside can't see a thing, and the whole panel is compromised.
So with all these problems, it was obvious something better was needed. The demand was there for a real upgrade. And that's where the hero of our story comes in. This completely new class of material.
Okay, so we're really talking about 2 main players leading the charge here. One is called aluminum oxynitride, or ALON for short. The other is magnesium aluminate spinel. We'll just call it spinel. These two are pretty much the peak of transparent armor tech right now. They're basically a window into the future of protection.
I love this quote from one of the research papers because it just nails it. It says this stuff has the optical clarity of glass, but the mechanical properties of a sapphire gemstone. Just let that sink in for a second. The perfect see-through quality of glass, but the hardness of one of the toughest gemstones on Earth. That's a total game changer.
All right, so how on earth do you make something like this? It sounds impossible, right? Well, the manufacturing process is a true marvel of modern engineering. It's all about turning a simple, fine powder into a see-through shield that's almost indestructible.
Okay, so here's how it goes. You start with this really pure ceramic powder. First, they press that powder into a solid block. It's totally opaque at this point. Kind of looks like a piece of chalk, and they call it a green body. But then comes the magic. This block gets cooked at insane temperatures. We're talking over 1800 degrees Celsius while being squeezed under immense pressure. After it cools and gets a final polish, what started as a block of chalk is now a perfectly clear, super dense panel. And the key to that whole transformation is a specific technique called hot isostatic pressing, or just HIP for short. So think about that chalky green body like a really dense sponge. It's full of microscopic pores, tiny little air gaps. Those gaps scatter light in every direction, which is why you can't see through it. What HIP does is use all that heat and uniform pressure to literally squeeze every single one of those pores out of existence, fusing all the grains together into one solid, transparent piece.
Okay, so that's the how it's made. But what about the why? Why is it so ridiculously strong? Well, the secret isn't some magic ingredient. It's all about order versus chaos on a microscopic level. It all comes down to its perfectly ordered molecular structure.
And this is really where transparent ceramics just leave regular glass in the dust. You see, glass is amorphous. Its molecules are all jumbled up, totally random, but these ceramics, they have this highly organized crystalline structure. And that microscopic order, that's the secret sauce. That's what gives it its incredible strength. This table really breaks it down. In glass, with its random structure, a crack has nothing to stop it. It just zips right through the material uncontrollably. But in the ceramic, the crack hits the boundary of one of those ordered, interlocking grains, and bam, it hits a wall. The structure forces the crack to stop, or at least change direction, which contains the damage to a very small area.
In fact, this stuff is so hard that when a bullet hits it, the ceramic doesn't just stop it, it attacks it. It literally erodes and shatters the tip of the projectile on impact. It's a phase called dwell, and it dumps a massive amount of the bullet's energy right at the surface, basically neutralizing the threat before it even has a chance to dig in.
So all this cool science is great, but what does it actually mean in the real world? Well, it translates into some game-changing advantages, especially for military applications where every single pound matters.
And here's the number that really tells the whole story: 50%. You get the exact same level of ballistic protection as traditional armored glass, but at half the weight and half the thickness. Let me say that again, half the weight. That isn't just a small step up, that is a massive, revolutionary leap.
And remember what we said about taking more than one hit. This is where it gets really dramatic. Old school glass is basically a one-and-done deal. But because the damage to the ceramic is so localized, the rest of the window stays intact. It stays strong. That means it can take multiple hits and still offer protection and visibility, which is absolutely critical when things get intense.
But it's important to remember, the ceramic itself is just the first line of defense. It's actually part of a team. It's a whole layered system. You have the super hard ceramic on the outside, the strike face, to shatter the projectile. Then there's a polymer interlayer whose job is to absorb the shockwave. And finally, a polycarbonate backing is there to catch any little bits of debris. Each layer has a specific job, and they all work together perfectly to stop the threat.
We're actually living in a new glass age, one where this everyday material has been totally re-engineered to be as strong and as functional as something like metal. It's a quiet revolution that's happening right in front of our eyes. Let's get into it.
And look, this isn't just some clever marketing slogan. It's signaling a really fundamental shift in how we build our world. The glass that you and I interact with every single day, it's no longer just this passive barrier to keep the rain out. It's become an active, intelligent interface. We've gone way beyond just simple transparency to create these functional, interactive surfaces. And this really nails the difference. Over on the left, you've got the glass we've known for centuries. Passive, brittle, you know the stuff. But on the right, that's where the magic is happening now. This new engineered glass is an active component. It's incredibly strong, and it's designed for very specific jobs. It's really the difference between a simple piece of material and a complex, high-tech device.
So, what's driving this glass age? What's the engine behind it all? Well, it's this incredible fusion of two fields: advanced chemical processing and nanotechnology. By being able to work at the atomic level, scientists can literally build glass with properties that, not too long ago, would have seemed like pure science fiction.
And this isn't some far-off future we're talking about. It's already here, right now. The screen on your smartphone, that's a structural shield. The windows on brand new skyscrapers, they're active thermal barriers.
But it's in transportation where we're seeing some of the most dramatic challenges. And of course, the most incredible innovations, especially when you start talking about aerodynamics. Which brings us to one of the trickiest and most fascinating problems in this whole field, the need for complex, curved glass. To get those sleek aerodynamic shapes you see on modern cars and jets, engineers first have to figure out how to bend glass in ways that were once thought to be completely impossible.
Which leads to the big question, right? How in the world do you actually do that? How do you take a material famous for being flat and rigid and force it into these wild, three-dimensional curves without it shattering into a million pieces or distorting everything you see through it?
Well, for the answer, we've got to look at the revolution happening in the auto industry. Car designers are pushing the limits, demanding these crazy wraparound shapes for everything from windshields to those huge dashboard-spanning digital screens. So let's take a look at how they pull it off.
Okay, so engineers have two main methods in their toolbox. First, there's gravity bending. This is the classic way. You heat up the glass and just let it sag over a mold. It's simple, it works great for basic curves. But for the really complex, aggressive shapes that modern cars need, they have to use press bending. That's where they soften the glass and then mechanically force it between two molds. It gives them incredible precision, but, and this is a big but, that process introduces a ton of stress. So the glass then has to be chemically strengthened afterwards to make it safe for the road.
And here is a perfect example of this in action, the windshield on the Ford GT supercar. Now, this is not just a piece of glass, it's a genuine high-performance component of the car's overall engineering.
Its construction is basically a high-tech three-layer sandwich. On the inside, facing the driver, you've got chemically strengthened Gorilla Glass. Yep, the same kind of stuff on a high-end smartphone. On the outside, you have standard Automotive glass. And then squished between them is a plastic safety layer. So what you end up with is a hybrid material meticulously designed for pure performance.
And this just shows you the payoff. This hybrid windshield is up to 30% lighter and way thinner than a traditional one. So why does that matter? Well, because it lowers the car's center of gravity, which directly improves how it handles and performs on the track. The glass itself is now an active part of the performance package. That's amazing.
But as impressive as supercar engineering is, believe it or not, it's kind of a walk in the park compared to the demands of an even more extreme environment, aviation.
Yeah, a supercar is one thing, but what happens when the stakes are literally life and death at 35,000 feet? The challenges for glass up there are on a completely different level.
Just think about it. An aircraft windshield has to handle a massive pressure difference between the cabin and the outside air. It has to endure insane thermal shock, going from freezing cold to heated up in just minutes. And, absolutely critically, it has to have zero optical distortion for the pilots. And on top of all that, it needs to have multiple fail-safe, redundant layers. There's simply no room for error.
So, to handle ice and fog, these windshields are coated with a really cool material called indium tin oxide, or ITO for short. It's basically a transparent metal that can conduct electricity, which turns the entire windshield into a giant, invisible heater. Now, applying this coating perfectly uniformly to a complex curved surface is an unbelievable engineering challenge. Any tiny variation could create a hotspot and compromise the entire structure.
So from our phones, to our cars, to the planes flying overhead, it's pretty clear that engineered glass is reshaping our world. Let's just zoom back out for a second and take a look at where this is all going. If there's one key thing to take away from all this, it's this. Glass isn't just a passive window anymore. The line between the material itself and the functional device that it's part of is disappearing. Glass is becoming an active, absolutely essential part of our technology.
Right now, we are firmly in the era of active engineered glass. But what's coming next is even more amazing. Researchers are working hard on self-healing glass that can actually repair its own cracks. And if you look even further down the road, they're talking about diamond-like coatings that can make surfaces pretty much indestructible.
And that just leaves us with a fascinating thought, doesn't it? If a material that we once thought of as the very definition of fragile could soon heal itself, what other impossibilities is it going to conquer? The science is all around us, hidden in plain sight, in the very glass you're probably looking through right now. You just have to wonder, what will it become next?